For those of you who don't know me, my name is Rob Fender, and I'm Head of Astrophysics here at the University of Oxford, and I would like to welcome you to the 2022 Halley Lecture in Astrophysics. The last time, the Halley Lecture series is an annual lecture series, which I'll tell you a little bit about the history of in a moment, but we haven't had a Halley Lecture since 2019 because, like the rest of the world, we were affected by the pandemic, and we chose, because these are such special occasions, we chose to keep these events as in-person events rather than going online during the pandemic. So this is the first one of these Halley lectures for 3 years. So I've had a little bit of fun looking into the background and the history of the Halley lecture series, and I'm just tell you a few things about it. So the Halley lecture series was founded in 1910 by the philanthropist Henry Wilde. And this was the reason it's called the Halley Lecture Series is because it was to commemorate the 1910 return of Halley's Comet. The subsequent return of Halley's Comet, of course, was in 1986. So you know, like probably several people in the audience, I was very disappointed by the 1986 return and didn't see a thing. And for the young people in the audience, of course, it will next be back in 2061. And the goal of the lecture series was to speak annually on the subjects of astronomy, astrophysics, and terrestrial magnetism. And the way we operate at Oxford at the moment is we have 2 astrophysics lectures interleaved every 3rd year with a lecture on the subject of terrestrial magnetism. So in looking into this lecture series, as I say, I found some interesting snippets of information, and I'll just share a couple of those with you before I introduce tonight's speaker. There is a paper in the February 13th edition of Nature in 1937, which recounts the first 27 years of these lectures. And it highlights the outstanding expositions given by little-known scientific figures such as Sir Arthur Eddington, Professor Henry Norris Russell, and Dr. Edwin Hubble. Eddington's lecture was delivered on May the 30th, 1930, with the subject, The Rotation of Our Galaxy, and expounded on the likely origin, form, and dynamical stability of our own Milky Way. Nearly a century later, in the 21st century, we find ourselves asking very similar questions, and those will be the subject of today's Halley lecture. Professor Amina Helmi is one of the world's leading researchers in the formation and dynamics of the Milky Way, our own home in the cosmos, and she's trying to understand very similar puzzles to those which Eddington was trying to understand nearly a century ago. Originally from Argentina, Amina received her PhD in 2000 from Leiden University. Postdoctoral positions followed at La Plata in Argentina, the Max Planck Institute for Astrophysics in Garching, and Utrecht University in the Netherlands. Since 2003, she's been faculty at the University of Groningen, and she has been a full professor there since 2014. There's a long list of prizes. I'm just going to highlight several of these, a small subset of these, in order to demonstrate her eminence. In 2004, Amina won the Christian Huygens Prize. In 2010, the Pastor Schmeitz Prize. In 2019, she won the Suffrage Science Award for Women and Science and Engineering. And in the same year, she won the Spinoza Prize in the Netherlands, which is essentially the highest award in the Netherlands for scientists, and joined the Royal Netherlands Academy of Arts and Sciences. In 2021, Amina won the Brouwer Award of the American Astronomical Society. She is the Netherlands delegate to the European Southern Observatory and is the scientific director of NOVA, which is one of the most important scientific organizations in the Netherlands. A component of our galaxy, the Helmi stream, is named after her, and I think we'll hear a little bit about that in Amina's lecture. So, ladies and gentlemen, without further ado, please join me in welcoming Professor Amina Helmi to deliver the 2022 Halley Lecture on the dynamics and history of the Milky Way.
Very much for this wonderful introduction. Let's see if this works. Yes, it's truly an honor for me to be delivering the Halley lecture. And what I wanted to discuss, as Rob was saying, is I want to tell you what we have learned in recent years about the history of the Milky Way using the amazing data set, new, vast, and amazing data set provided by the European Space Agency mission, the Gaia mission, that is currently mapping the Milky Way in extraordinary detail. So while I was preparing the lecture, I thought it would be good if I could show a link between, Halley and the work that I'm presenting today. And just like Rob, I was disappointed in the sense I was 15 years old when the comet was supposedly visible. I was living in a city in Argentina, and of course with the lights, it was even really, really hard to see it. So I didn't get to see it at the time. But as I was doing some research on the comet, what I discovered is that the comet is on a trajectory, as you can see in this movie. So it comes from very far. It is on a very elongated trajectory. And it's moving in the opposite direction as the Earth around the sun. So what you can see, let me see if I can point it here. The comet is moving in the clockwise sense, and the Earth is moving anti-clockwise. It's also on an inclined orbit with respect to the plane of the solar system where the planets are orbiting, and it's on a very elongated orbit. And it turns out that one of the objects that I'm going to be talking about today that was very important in the history of the galaxy actually shares similar dynamics. So that's the link. Okay, so what is the Milky Way? The Milky Way is a conglomerate of stars, gas, dust, and dark matter that are held together because of gravity. And around the Milky Way, we have small galaxies that orbit around it. And this plane that you see on the sky on a bright night, you see this whitish band on the sky, is made of billions of stars, hundreds of millions of stars that are just too faint to be resolved with the naked eye. But with a space mission like Gaia, you can actually see these individual stars, and you can measure the properties. And on an image like this, you see these very dark regions, and these dark regions are the places where new stars are being born, and with these stars, planets, and of course, comets. So the Milky Way, in fact, is a rather typical galaxy. It's one of billions of galaxies in the universe, and there's, in fact, in terms of its type, so it's a disk galaxy. We're sitting in that plane. That's why you see this band of stars on the sky. It turns out that 2/3 of the galaxies in the universe, of the large galaxies in the universe, are disks. The Milky Way is rather typical also in terms of its brightness, its size. So there's nothing special, you would say, in that sense. But because it's so typical, actually, it can be used to understand how, in general, galaxies form. We can also use it to understand what the physical processes, which physical processes are important in the universe, are playing a role in, say, galaxy dynamics or in galaxy evolution, and also what the universe is made of. We know that most of the mass in the universe is in the form of dark matter. We can use the Milky Way, the motions of stars in the Milky Way, to try to put constraints on what this dark matter really is. But the reason I'm interested in the Milky Way is, as Rob was saying, is it's actually our home in the universe. And of course, we are all interested in understanding our own origin. And so that triggered me to want to study the history of our galaxy. What is the history of our home in the universe? And so we have a fairly good idea of how structure developed in the universe. Starting from the Big Bang, the universe expanded. As it expanded, so that's depicted here. As it expanded, it cooled down, and density fluctuations present in the very early universe, grew in mass and in these density fluctuations, the first stars and the first galaxies formed. Right? So what we're plotting here is we start from the Big Bang and we go all the way out to the present day. So we are now we've been able to look at distant galaxies with the Hubble Space Telescope, and now with the JWST, the Just Wonderful Space Telescope, we're able to see very distant galaxies, and what will be happening is that we will learn a lot more about these very distant galaxies in the coming years, but for the time being, at least with Hubble, all that we knew about was that these systems were there very early on in the history of the universe, but we didn't know much about the properties. We knew there were blobs forming stars, basically. So the fact that they are there tells us a lot, but at the moment we don't know so much about the properties of this system. And as you go closer and closer to the present day, then what you can map populations of galaxies, and what you see is that many of these galaxies are interacting. And then you can come to the present day where you see galaxies, say, in adulthood. So the Milky Way has fully formed. It has different components. And one thing that one should realize is that some of the stars that we see in the Milky Way actually were born around the time that we see the farthest galaxies in the universe. So these stars were born under similar conditions, under the conditions that were present at very early times. And so they tell us about how the universe looked like at those times. And so they can be used to try to figure out how they're witness, basically, of the process of formation of a galaxy. So we can use this fossil record that we are currently mapping in extraordinary detail to try to rewind the movie backwards and to try to figure out how the galaxy was put together. And currently, this is not possible for other systems because it's very hard to measure many properties of individual stars in distant galaxies because we just can't resolve the individual stars. This might become possible, for example, with the big telescopes that are being built at the moment, such as the Extremely Large Telescope. So the Milky Way is like a Rosetta Stone, and we can try to use it to figure out galaxy formation in general. And as I was saying, the Milky Way has different components. So we have, of course, it's a disk galaxy. So most of the stars are actually in this disk. And the stars in this disk, so we're currently forming stars at about 1 sun per year, roughly. And these stars in the disk, they move on very ordered motions. They move on circular orbits, and they say retain this, maintaining, say, this disky structure, this very flattened structure. Then we have the thick disk, which is slightly, so these stars have slightly less ordered motions, but they're also older, and they have a different chemical composition than the stars that we see in the thin disk. Then we have the stars in the bulge, which are probably where we find probably some of the oldest stars we know of. And then what we have is the halo. Stars in the halo actually move on very elongated orbits because in that way you can probe very distant regions. It's a spheroidal component, and here is where we find the most pristine stars. So the oldest, and also the stars that have the least amount of chemical elements, except, of course, hydrogen and helium. And so because the distribution, so what we're seeing is that the stars are distributed in different components, and these different components, these stars have different characteristics. So this gives us clues about the process of forming of the galaxy. And if we look at a numerical simulation of how we think galaxies form, of course, initially the universe is relatively smooth. And then the first small galaxies start to form. The first halos start to collapse. And then you begin to get gas onto these potential wells. And then you start forming stars. And so what you see is at very early epochs, you see a lot of activity, small galaxies. They come together because of gravity. And in that way, you produce larger and larger systems. And at some point, you produce, disks are produced. This is, in fact, a movie of the formation of a disk galaxy, something like the Milky Way. And these mergers continue, but what you see is that most of the merging activity takes place at early times. So as we go back, we come to the present day, fewer and fewer such mergers take place. So one question that, of course, we ask is this also the way the Milky Way formed? I mean, this is a model, right? Can we actually test this? How do we figure out that this is the way our galaxy formed? And that field is now known as galactic archaeology. And so the idea is that stars actually remember where they come from. They remember where they come from in terms of their motions, actually. Their motions tell us where they come from. They remember where they were born, and that we can reconstruct on the basis of the chemical composition of the elements that we see, the abundances of the different chemical elements that we can measure in the atmospheres of the stars. That reflects the cloud in which the stars were formed. So it tells us about the environment in which the stars were formed. And from the ages, we can tell when the stars were formed. So with all of that information, we can try to reconstruct the history. And so if you take snapshots of a simulation like the one I showed you, remember at very early times, we had lots of small objects. The first galaxies were small, and then they came together because of gravity. They produced larger and larger systems. The small ones get destroyed. They produce these substructures and tidal tails. And if you look at the present day, what you see, of course, is a disk. And most of the stars in the disk of the Milky Way formed in the Milky Way itself. But the stars in this halo component actually came on board these small building blocks, these small galaxies. And so one of the characteristics of the model, as you saw in the movie, is that mergers must have been important in the past. And so we would like to know how important, how many, when did they happen, and do any of these building blocks, do they have anything in common with the small galaxies that we see around us today? Can we tell if there are any differences? And so the best place to look for, say, the remains of these objects, what's the leftovers of the mergers that the galaxy experienced, is basically the stellar halo. So if you take a numerical simulation and you color code the stars in the halo by their progenitor, so each one of these different building blocks, you give it a different color, what you actually can see is that at very large distances, the stars are distributed in substructures, right? You can tell from the distribution in space of the stars that there have been mergers. But if you look at the inner regions, it's all mixed up, right? You can't tell one star from the other. And so how do you actually tell that these stars came on board small systems? So if we zoom in on what happens when you have a merger, so this is what this simulation shows, is you have a small galaxy, and this is torn apart by the tides that it experiences because of the Milky Way, because of the presence of the large galaxy. So it's just like tides deform, say, the Earth. Tides will also lead to the disruption of the small galaxies. And one of the things that you notice here is that if you wait a while, If the stars had not been painted in red, you wouldn't be able to tell from the spatial distribution, actually, that these stars came on board an object, a satellite galaxy. But what you can actually see is, if you look at any location in space, what you see is that the stars are moving together through space. They are defining streams. And it's through mapping the motions of these stars that we can actually tell that these stars were not born in our galaxy, but they were born elsewhere. So how do we find streams? So if we take one snapshot from that numerical simulation, right, that's shown here, say we are at the position of the sun, and we would look at how stars are moving through space, then what you actually see in this particular snapshot is there's a group of stars moving towards, say, upper right, a group of stars moving towards the upper left. So if you would plot one velocity against the other, right, you would see two groups of stars, right, two moving groups or streams. Now you can go one step further and you can say, okay, but initially all of the stars had the same position. They were all together clustered in space, and they were moving together through space, right? So they had a similar trajectory, so they had similar energies, and they had similar angular momentum. They were rotating together or moving together around the galaxy. And so if energy and angular momenta are conserved quantities, so quantities that don't change in time, then what happens is that initially all of the stars are together in a space of energy and angular momentum because they're all clustered in the same space. And if these are conserved, then if I take another snapshot I look much later in time, the stars will be in the same place, also defining a clump in energy and angular momentum. So if we go back to this idea of trying to disentangle the history of that stellar halo, of course, stars don't come with flags that tell you, no, I was born in this galaxy or in this other one, so it's all black and white, if you wish. If you look at the kinematics, then we would see lots of small moving groups, lots of streams. And if you look at the space of energy and angular momentum, each one of the galaxies would define a clump. And you can already see that even if you didn't have these colors, if you run a clustering algorithm on this data set, even if this was black and white, you should be able to see the individual clumps, the stars that are associated to the different objects that the galaxy has cannibalized. So we've known this for about 20 years, but it took a while before we had the data in which to test this idea. That's because our knowledge of the Milky Way, and in particular, having motions, having measurements of how the stars move through space is extremely difficult. And so our knowledge until before the launch of the Gaia mission, basically we only knew how stars were moving through space in the vicinity of the sun, in a very small volume around the sun. But with Gaia, the horizon became much larger, and now we can really probe a much bigger region around the galaxy, and we have many more objects. We have a volume that's about 100,000 times bigger. We know the motions of the stars 100 times better than we knew them before, thanks to the Gaia mission. Gaia was actually, and you can imagine that with these factors of 10, you're ensured that a revolution will be triggered. And in fact, that is what we're witnessing. So these Gaia data releases that have the properties of stars, of about 2 billion stars in our galaxy, are really changing the field. In the latest data release of the Gaia mission, what we have is lots of information about where a star is located in space, so the three-dimensional distribution of stars. We also have the measurements of the motions of stars on the sky, and also for a fraction of the stars, we know how they move with respect to us. For many of the stars, we also have their properties, such as how hot they are. And also we have chemistry now for a fraction of these stars. So this is a very, very large data set, and it's extremely impressive that we have been able to map the galaxy in this amount of detail. And one of the things I like about the Gaia mission is that there's a lot of different science that you can do with such a data set. So just, I discussed the motions, but just knowing the temperature, knowing the distribution of say, the chemical abundances of stars, there's a lot of information in there. And so there's a lot of science because Gaia observes everything on the sky that's down to a certain brightness, down to a certain magnitude. So it's not only stars, it also observes galaxies, it observes quasars, it observes objects in the solar system. So the science is extremely broad that you get from such a survey mission. And so we've been learning a lot about, say, the universe around us. And in particular, some of the things I've been involved in are, we've been learning that the Milky Way is actually a system that's not in equilibrium, that's responding to its environment. So often in, I guess, in astrophysics or in physics, one might think things are in equilibrium. The Gaia data has shown us we shouldn't think about this, about galaxies in this way. We see signatures of disequilibrium. We see signatures that the Milky Way is still evolving, and we need to take that into account. We can use the motions of stars to map the distribution of dark matter around our galaxy, and also dark matter in the satellite galaxies around the Milky Way. Gaia has also discovered some of the brightest quasars, so it's an incredibly broad data set. But really the reason the Gaia mission was built was to try to answer this question: how did the Milky Way come to be like this? And as I was saying, with Gaia, basically, what we're seeing is that everything moves. So we're really able to measure the motions of so many stars in our galaxy. And from this, we're able to derive their site of origin, as well as the forces that drive their motions. Okay, so that's an introduction about Gaia. What did we actually find in this data set? And so before I describe this, what I wanted to do is I want to make sure we're all in the, on the same page. So I'm talking about velocities of stars. So let me describe a coordinate system. So we have our galaxy, the plane of our galaxy. We have the sun, 2/3, say, in the outskirts of the disk of our galaxy. And we're going to be looking at stars that are near the sun. And so the stars can move. If they're in the disk of our galaxy, they'll rotate mostly, right, in ordered motion. So that's the v phi component of the velocity. But they can move up and down. That's the vertical component, vz. And they can move in the plane in the radial direction. And so stars in the disk will show mostly rotation and very little random motions. Stars in the halo will show very large random motions and little rotation. At least that's the expectation. So what did we see? So here's a plot showing rotational motion versus random motion. Most of the stars in our galaxy are in the disk. They move like the sun in order motion. So most of the stars are here, right? You see this very dark region. We didn't plot the individual points because it would just be black. So most of the stars are in the disk moving on regular circular orbits. As you move away, you go into the regime of the thick disk. And if you go further away, so you're rotating less, you have more random motions, you go into the region where the halo stars are. And what you see here is that in this region, you have basically two components. You have this stars that seem to be the tail of this distribution. This seems to be like a thick disk. And you have this very big blob here. And what's interesting is that a fair fraction of the stars are actually moving in the opposite sense as the majority of the stars in our galaxy. The majority of the stars of the galaxy are moving clockwise. But there's this component that has a mean velocity that is negative, that's moving in the opposite sense. And it's not a negligible component. It's quite a large fraction of the stars. And then what you also see is this arc that is here. So what we did is we then look at the chemistry of the stars. And one way of looking at chemistry of the stars is by looking at the elements that are produced on different time scales. So produced by massive stars that explode very quickly compared to stars, to elements produced on, say, longer time scales. And typically the evolution in a space like this is flat and then it goes down. And what we found when trying to understand what this component was that the stars in that component defined a separate sequence in chemical space. This is the thin disk, this is the thick disk, and this is that component. And immediately as you see this, what you know is that these stars were not born in a galaxy. You can actually tell that these stars were born in a different system. You can tell how massive that system was. And so basically what we found is that the galaxy experienced a merger about, we can also measure the ages of the stars. So it experienced a merger about 10 billion years ago. What we also know is how the Milky Way looked like at the time. We know there was a disk at the time. So we know that this merger kind of also the configuration of the merger, because the fact that the stars are on slightly retrograde orbits, the fact that you have an arc here actually tells you what the configuration of that merger was. And so this, what we discovered basically is really a milestone in galactic history. This is the last big merger that the Milky Way experienced. And this movie shows how we think that merger happened. So we had a disk-like galaxy at the time. And because this object was so massive, it shook the galaxy, it heated it up dynamically. And it also induced a lot of star formation in the system. So this merger not only led to the formation of the stellar halo, where a large fraction of the stars come from this one object, but also led to the formation of the thick disk of our galaxy, both dynamically as well as triggering a lot of star formation at the time. So because this was so important, we gave it a name, and we gave it the name Gaia Enceladus. And Enceladus, because it's a giant in Greek mythology, and this was a large galaxy that fell in. It turns out that Enceladus is the sun, in Greek mythology, is the son of Gaia and the sky. The myth says it's buried under Mount Etna, and it's responsible for seismic activity. And if you think about it, it's buried in the Milky Way, buried in the Gaia data, and it was responsible for quite a bit of shaking of the galaxy at that time. So we found we found the big fish, right? And it's moving retrograde, and it had a different chemical composition, which allowed us really to figure out how this merger happened. But is there anything else in the halo hiding? Is there any other evidence of merger debris? So, as I said, one of the best ways to look for merger debris is to look at this space of energy and angular momenta, right? And so this is where we expect to find lots of clumps associated to the different objects that fell in. And so what we did is we ran a clustering algorithm on this space, and what we found was many different clumps. This would be, say, the region associated to Gaia Enceladus. We found lots and lots of sometimes larger clumps, sometimes very small ones. And what we're doing at the moment, and that is where, again, the archaeology comes back, is you should realize these are stars that were formed in other galaxies outside of the Milky Way in the early universe. So these are the stars that built the halo of the Milky Way. And if we can characterize, we can put these stars together, we can characterize their properties, then we will be reconstructing the history of the progenitors, of the ancestors of our galaxy. And so we're really doing archaeology in the sense of you're using the remains, you're using the leftovers to try to reconstruct history. And so what are the things that we found? So one of the things you can ask yourself is, for example, did the galaxies, are these clumps that we're seeing in energy and angular momentum space, are they the remains of star clusters or globular clusters? Are they the remains, do they look like the dwarf galaxies around us, like the dwarf spheroidals? These are very faint dwarf galaxies. Or do they look like objects, more like objects like the Magellanic Clouds, these big satellites around the Milky Way? So one way of trying to figure this out is not just by looking at the size of the clumps in this space of energy and angular momentum, but also by looking at the properties of the stars. So if you actually plot a diagram, this is called the color magnitude diagram. So you plot for each individual star how bright it is, and also the difference in brightness in two different wavelengths, two different wavebands. What you see is that if stars were born at the same time and they had a very similar chemical composition, the stars define a very well-defined, a very narrow track in this space, where the position of a star is dependent only on how massive the star is. So stars in a globular cluster, we think they're all formed together because we see them basically following just a single sequence. And some of the clumps that we see in the Gaia data, in fact, also follow a single sequence in this space. So we are discovering that some of the clumps that we're identifying are probably due to objects like this that were disrupted a long time ago. For some of the other clumps, such as the Helmi streams that you were referring to, Rob, what we see is that although they follow this distribution, of course, you see that this is much broader, right? And so that tells you that there were many generations of stars that were formed in this system. We also see that there is a range of, in this case, iron abundance, so that also you need several generations of stars. And what we can now do from the distribution of stars in this color magnitude diagram is we can infer how many stars were born and when. And so that tells us how star formation proceeded in this object. And this is actually shown here. And what we see is that this galaxy was a bit slow in forming stars, much slower, for example, in comparison to this large system that we call Gaia Enceladus. So in this way, we're kind of reconstructing the puzzle and figuring out how these galaxies that were accreted long ago were formed and evolved. What we're also finding is that these galaxies did not fall in on their own, but they had companions, they had globular clusters of their own. So actually, if you look at the distribution of globular clusters, again in energy and angular momentum, so these are the globular clusters that are of the Milky Way now, and you're asking where were these clusters born? What you actually see is that they were born, many of these were born, they came on board, say, these large galaxies that were accreted. So roughly half of the globular clusters in the Milky Way apparently were accreted, the ones that survived, but a very large number of clusters seem to have disrupted. And these disrupted clusters are giving rise to a very large number of very thin streams that people are discovering around the galaxy. And these very thin streams themselves, so they came on board, say, star clusters, they're also associated to the different overdensities that we're picking up, again, in energy and angular momenta. So we are kind of reconstructing the history in the sense of we're figuring out how the progenitors of our galaxy look like. At the moment, there are something like 6 different objects that have contributed in different ways to the stellar halo near the sun. And we're trying at the moment to reconstruct what their properties are. And we're seeing that they didn't come on their own, but they had their own, say, clusters around them. And these clusters are also contributing to our galaxy today. So all of this work would not have been possible without the help of, or without the work, actually, of many PhD students and postdocs. Here we are in Groningen, celebrating the release of data, the Gaia mission, data release 3, last June. But I think most importantly is the contribution of about 500 astronomers and engineers scattered throughout Europe, all of whom work together to produce the amazing data set that is publicly available, that everybody can go and work with and explore, that is the Gaia mission satellite, the Gaia data set. So if I have to summarize what we've discovered is we've uncovered merger events that happened in the last 10 billion years or so. We're beginning to characterize them. We're seeing, we saw this very big merger that took place 10 billion years ago, what an impact it had on the Milky Way. We're seeing smaller objects, and we're reconstructing their properties. But we would like to know what happened before, say, even before 10 billion years ago, what happened really in the youth of our galaxy. And so if we want to do that, there are a couple of things we need. We need data. We need to move away from the vicinity of the sun. We really need to explore the whole galaxy. And we need, as you saw, chemical information is extremely important to figure out where a star is born. It's like the DNA of a star. It gives you an imprint of the environment in which this was formed. And there are new data releases coming out from the Gaia mission in the next year, so we'll be able to probe a much larger volume. But we're also building new instruments, we call multi-object spectrographs, that can measure the spectra, and therefore they can measure the chemical compositions of the stars for millions of stars in our galaxy. And with these data sets, both WEAVE, that's actually built here in Oxford, that will be placed in the Canary Islands, but also foremost in the southern hemisphere, that will be placed on the VISTA telescope in Chile, will have a much more detailed map of our Milky Way, and we'll be able to push or rewind the movie back even further. So if there's one thing that I would like you to remember from this lecture is that we're sort of working out, well, Gaia is actually helping us understand how the night sky was put together. So the next time you look up, remember that, because the fact that the Milky Way had a big merger, such a long time ago, means that it actually had time to develop a disk or to maintain a disk with the characteristics it had. If the merger had happened more recently, or if the merger had been more massive, then the galaxy would have looked completely different, and so the night sky. I'll stop there. Thanks very much.
Thank you very much. Thank you very much, Amina, for this fantastic and beautiful talk. Let me abuse chairman's privilege by asking the first question, and it's going to be a naive and probably embarrassing one. I don't work in this field at all, so I've learned a lot tonight. So we've been consuming satellite galaxies for 10 billion years. But we have these two small nearby galaxies, the Magellanic Clouds. How have they survived?
We think they've fallen in very recently, actually. We think they are on the first passage around the Milky Way. And what we are seeing the tidal effects. We're actually seeing how gas is being lost, being stripped by the Milky Way. And, yeah, we also see the interactions between these two galaxies. We think they will fully merge in about 4 billion years into the future.
Okay, thank you very much. Questions in the room?
Hello. I was wondering, when modeling the dynamics of merger events, so Gaia gives you some very good, phase-space distributions of, say, your two galaxies, right? Do you have to assume that those distributions are also representative of the distributions of the respective dark matter?
No, in fact, right? So we think dark matter should be much more extended than the stars. So the distribution of dark matter ought to be a lot smoother. The simulations, I should have said, the little movie that I showed of the merger, actually, we had that movie in-house. It was meant to do something else. We were using it to try to figure out the formation of the thick disk. We never thought this would be a way of figuring out how the halo had formed. So it's not tailored to reproduce the observations. In fact, the way it worked is we saw this plot showing that I showed with the velocities of the stars. Here, this plot. And then I remember that a PhD student had made a similar plot from simulations 10 years earlier that looked very, very similar. And that triggered the idea of, and these mergers in these simulations, so these simulations do have dark matter in them, but what you start with is with a disk. And so two disks that merge, and the dark matter also merges, and in the end forms the whole halo. It's not, I don't think there has been any simulation that has really tailored to reproduce these properties.
Thank you.
Let's just quickly see if there are any questions online. I gather there's a lot of people online. Amina, can you read some questions?
Yes,
Okay, thank you. We have a first question asking, how much does the chemical composition of stars from different galaxies differ? And whether you could give some examples of the differences in which previous dwarf galaxies they would correspond to.
Yeah, so there's a couple of ways in which they differ. So we know there is a mass metallicity, so it's a mass and the abundance of iron in the universe. So there is a mass metallicity relation. So smaller galaxies have the stars have less iron on average. And the other thing is that in smaller galaxies, it seems harder for them to form stars, so the star formation rate is lower. So you also get a different imprints in other chemical abundances. And we see this both in the satellite galaxies that have survived, as well as in these building blocks, that the chemistry is really that they follow different tracks in chemical space. So there's enough information potentially to actually figure out, once we have for very many stars chemical abundances, to really figure out the different objects that fell in and how they evolved.
Let's see if there are other questions in the room. Yes.
Earlier, at the beginning, you mentioned the Milky Way was a typical galaxy. Did you mean along like the temporal dimension, in the sense that atypical means younger or much older, about to expire, or is there other ways, examples of atypical galaxies?
Yeah, so I guess I was referring to in terms of how large it is. It's a galaxy that has a disk. You can have galaxies that are more elliptical, right?
So in shape.
There's galaxies that are interacting, so they look very irregular. So disks are very common in the universe. Large disks are common. And I guess you could say they all kind of form stars at present day, probably at a similar rate, although there are differences. So in that context, it's typical.
Thank you.
Do we have other questions in the room, Ray?
Yes, thank you. So people often ask me, how old is the Milky Way? They want to know how long has things been going on. And so if you look on NASA websites or whatever, you get numbers like, I don't know, 16.1 billion years. But it seems to me from what you've been describing, we're a merger of many, many different small galaxies, different ages. What do people actually mean, if anything, when they ascribe an age to the Milky Way? And is it even a sensible question in the light of the new things?
Yeah, that's a very good question. I think if you, as I said, most of the stars in the Milky Way are in the disk. So if you have to give an age, I would say at least you can say what the age of when that disk, where are the oldest, how old are the oldest stars in the Milky Way, in that disk. And that is about 8 billion years old. So all of this activity happened before, say, that thin disk was in place. But indeed, it's very hard to say how old you are if you're from bits and pieces. I think at that point, so 8 billion years ago, basically history turned out to, it's like, during the youth of galaxies, a lot of things happen, and at some point you reach adulthood, and then you evolve more or less slowly.
Thank you. Yes.
Toward the end, you mentioned there are 6 or something building blocks. Could you summarize the mass ratio and the timing of the merger of these events?
Yeah, so that's a good one. We're not fully there yet. I think the biggest one is, of course, Gaia Enceladus, which is about, I would say, 10 to the 9 solar masses in stars. And that was a 1-to-4 mass ratio because a long time ago, the Milky Way was smaller. The other ones are a factor 10 or more smaller. So 10 to the 8, so the Helmi streams we think are 10 to the 8 solar masses. And the other objects that we're finding are a few times 10 to the 7 or even lower. In terms of when they fell in, I don't think there has been a lot of dynamical modeling to say this. And so there's 2 ways in which you can look at this. You can ask, when did these objects stop forming stars? And that might tell you when they fell in, because as soon as you fall in, maybe you lose the gas, the fuel for star formation. And so the oldest stars in the Helmi streams are about 10 billion years old. I think you can see that from the star formation history. But if you look at the dynamics, you would actually say it's fallen in more recently, between 6 and 8 gigayears ago. And then the other objects, I would say, yeah, probably around the same time, something like between 8 and 10 gigayears ago. There are some objects that are very deep in the potential well, so probably fell in earlier. But it's a bit, we don't yet have star formation histories for everything, so we don't know yet. But the idea is indeed to try to do this kind of work, yes.
So your talk's generated a lot of questions, so we can get a couple more. So we have some more online questions.
So can we know anything about the black hole in the middle of our galaxy from this kind of data?
I guess not from this data, but you can ask yourself, how do these black holes, form? And in principle, we think every respectable galaxy has a supermassive black hole in the center, and so through mergers, these black holes would also eventually make it through the center. So maybe in the inner regions, the central regions of, for example, Gaia Enceladus, there was also an intermediate mass black hole, probably. Yeah, it's a lot harder to track the history of black holes, of the growth of black holes, than of the galaxy itself.
One more online question.
So, how might the differences in the chemical compositions of mergers and the stars born in our galaxies differ in their later stages?
In the early
In their later stages. So, how might the difference in the compositions of mergers and stars differ in the later stages?
Yes, so I guess in the early stages, so what you have is you have lots of massive stars explode. These are the first ones that will explode and will contaminate the medium around them. And so you have a lot of elements produced by those stars. And as time goes by, you know, these stars will have been gone. The massive stars explode quickly, and then you have the more common stars evolve. And so what you get is other chemical elements come into play at later times. And the enrichment, depending on how many stars you form, the enrichment might proceed rather slowly, actually.
I'm afraid we probably have to wrap it up there. Before we thank Amina again, let me note for those of you who are signed up and coming along to the dinner, who don't have their own personal transport to get over there, that there is a bus with space for everybody to take them from here over to St Hilda's where the dinner is. And so let us thank Amina again for the wonderful Halley lecture.